Thank you for joining for this second part of pre-calculus graph parent functions. We took a look at graphing the base 2 exponential function as well as logarithm base 2. Let's take a look at two other examples to round out this section. Let's share the screen and head to our notes. So our third example for graphing parent functions is something that we saw first in Algebra 2. So here our task is the same. I want to graph each parent function by creating a table of coordinate points. So we'll begin by creating our table. And we'll label that left column X. Those are our independent values. F at X is the label for our right-hand column. And again, those are Y values. We call it F of X to say that they come from X. They depend on what the X value is. So for this function, like we've seen with others, we'll choose the traditional -2, -1, 0, 1, and 2, those 5. Again, centered around the origin. Let's calculate the outputs for these 5. So our function here is f of x equals a fraction, 1 over x, and x is in the lower part, the denominator of the fraction. So our first evaluation is going to be f at -2. So just like we'd seen with our first two examples, we're just replacing x with that specific value. So this becomes 1 over -2, and as a decimal, that's -0.5. Let's record this over here on the left. So -2, -0.5. Next, we'll evaluate f at -1, which is 1 over -1, and that reduces down to -1. So our second point, -1, -1. Now let's calculate there at 0. So right there on the y-axis, we're wanting to see what's the y value when x is 0. Again, we'll substitute, and we run into a problem. We have 1 divided by 0. So we have to think, and it's good to think in terms of real-life items. If I were to give you a pie or a pizza, and gave you instructions to cut that pie, cut that pizza into 0 pieces. At that point, we have to say that's impossible. And so for a different reason than we saw when we were dealing with logarithms, but still the same label, we're going to say that that's undefined. Algebraically, that's not something that we can do. We'll see how that undefined value at 0 shows up on our graph. We'll also calculate now for these positive values. So 1 becomes substituted 1 over 1, which is +1. So we do have a point here in quadrant 1, 1, 1. And last value here on our table is f at 2, which is 1 over, instead of x, I'm going to write 2, which is 0.5. And that completes our 5 points. So we'll go ahead and graph those here on our coordinate plane. So -2, that's +1/2. Where should that have gone instead? Good, should be down half. -1 is at -1. And then the undefined value here at the x value of 0, again, because I know this function, I know that that's a vertical asymptote. So we're seeing some similarity here between this function, which we call the rational parent function, we can name it, and the logarithmic base 2 parent function. Let's see if there's any other similarities or if there's other differences. So we got that vertical asymptote again. It came from the fact that this was undefined at the y-axis. And now we're in quadrant 1. So +1, +1's there. And at 2, we're at half again. So a very kind of piecemeal framework that we've got here. Now, one thing that I want to offer is just kind of an overview of the tools that you've got at your disposal when you're working on graphing functions and doing algebra online. So we can do this stuff, creating the table, plotting the points, getting a framework manually, But we do also have access to a really good free online calculator that really gives the TI-84 or the TI Inspire a run for its money. Those cost a lot, and this calculator does everything they do, but it's free. So I'm going to share that screen. So this calculator, I'm going to highlight the URL line, is www.desmos.com. So that's going to take you here to this gateway site. And to get to the graphing calculator, you're just going to hit graphing calculator from desmos.com. And what I'd like to just offer is a way for you to see how we can use the graphing calculator to fill out our framework. So we'll wait for that to load. And once I get to this graphing calculator view, what I want to do is input the function over here on the left in that line labeled 1. So I'm going to just type in f parentheses x close parentheses equals 1, and then you can use the slash key there with the question mark to get a fraction over x. And just to show you what's available, you do see that curve. So it's a curve maybe you recognize, maybe it's unexpected based on the framework points we'd put in. Just to show how you can get a table from Desmos, if you go to that cog, the edit list, and then go down to your function line where you input your f of x equals 1 over x, click convert to table, and you see the same table that we generated manually. Desmos is offering it here through those 2 clicks of a button. Well, I see that the graph exists here in quadrant 3 on the left and in quadrant 1 on the right. I do see that vertical asymptote at the y-axis. And I also see, surprisingly enough, a horizontal asymptote on the x-axis. So this one looks like it has 2 asymptotes. Well, with that picture in view, I'm going to head back to our notes screen. And I'm going to sketch in that graph based on what we saw on the Desmos graphing calculator. So I'm going to sketch in a horizontal asymptote on the x-axis. And then I'm going to sketch the actual graph here starting in quadrant 3. So the graph starts over here on the horizontal asymptote and then veers down and follows the vertical asymptote. The other branch of the function starts up in quadrant 1, on the right side of the vertical asymptote, and it also veers to the right and hugs that x-axis, the horizontal asymptote. So an unusual function that has 2 separate branches, 2 separate pieces. That completes our graph. Now, we had some information. So we'd said, okay, I've got a horizontal and a vertical asymptote. So I'm going to start naming them. The horizontal asymptote. And again, I'm going to write this on the graph itself. On your work, you can put it on the graph or below it. Definitely H.A is a good abbreviation for horizontal asymptote. So again, all those y values are the same. They're all 0. So I'm going to name it y equals 0. The vertical asymptote is the y-axis. So again, I'll abbreviate VA for vertical asymptote. And again, I want to name its equation. So on that y-axis, all of the x values are good, 0. So I'm going to name it x equals 0. So that takes care of these 2 analysis items. We caught the horizontal and the vertical asymptote. Now we need to think, if I've got a vertical asymptote and a horizontal asymptote, will I have any y-intercept? Will I have any zeros or x-intercepts? Again, to think about an asymptote is to say the graph doesn't touch it, it doesn't cross it. And so what we can say is there are no zeros, no y-intercept. So again, part of the graphing, part of the analysis will inform you about other parts of the analysis that you have yet to complete. What that leaves for us is domain and range. So remember, domain is a description of, can you remember? Good, the x values of the function. So when I look at this function from left to right, negative infinity is there, the left extreme, positive infinity is the right extreme, and the vertical asymptote's at 0. Now, because there's two branches, two separate pieces to this rational parent function, my domain has to represent that by having two pieces in the domain. So we'll start here on the left. This piece that's down here in quadrant 3 begins at the far left at negative infinity, that's x, and travels all the way to 0. Now at 0, it descends and plummets down forever. But the second branch picks up on the right side of 0 up here in quadrant 1. So we would begin the second piece with 0 and again say it's less than x and it's less than infinity. Now we have two branches. So the word that we would put in between them is the word and. Why can't we just put them both together? Good, the vertical asymptote's in between those two branches. That makes us have to have two separate parts. Now let's write that in a more efficient way with the interval notation. So negative infinity, parentheses, negative infinity, comma 0. And then we'll deal with that word and in a moment. So I'm going to pick up the second part, parentheses, 0, comma infinity. And the symbol algebraically that we would use to signify the word and is this symbol, the union. So those are two ways to write the domain. One's in the inequality notation. The second's in interval notation. There are advantages, disadvantages to each. Let's finalize this example by writing the range. So that is the y value. Now there's a real symmetry to this rational parent function. The lower part of the graph's infinity, I'm sorry, negative infinity, the upper part's infinity. So our range, like if we think about how it compares to the way we wrote domain, it's really the same because those two branches are very symmetrical. The y values start at the lower part of the graph. Negative infinity is less than y is less than 0. Again, 0 is both for the vertical asymptote and the horizontal asymptote. And 0 is less than x, y is less than infinity. So the only difference is the variable. Note that when I go to write the interval notation, parentheses, negative infinity, 0, comma, parentheses, union, parentheses, 0, comma, infinity, close parentheses, that's identical to the interval notation for our domain. And to me, that's one disadvantage of interval notation. I like it because it's efficient, but notice it doesn't include the variable x or y. All right, so that completes our analysis and graphing of this rational parent function. And let's see our last example. So one more example here, fourth example of a parent function. And let's look at one of these, what we call power functions. So here we've got f of x equals x to the power of 4. We'll create our table. So we'll put x there in the left. So again, -2, -1, 0, 1, and 2. F of x. And let's calculate this, see if we can do it manually. So we're going to say that the base is our x. So it's kind of the opposite of an exponential function. Exponential function, x is in the power. Power function, the x is in the base. So I'm going to substitute -2 in here to the power of 4. Now I write parentheses. That's important Because literally this is -2 times -2 times -2 times -2. Now to deal with that product, I'm going to pair them up so I see what happens to the negative sign. So a negative times a negative is a positive. 2 times 2 is 4. So this is really 4 times 4, which is 16. -2 comma 16. We'll keep going, f at -1. So again, we're going to see that pattern of pairs of negative numbers multiplying to become positive. So each of those pairs is going to become +1. 1 times 1 is 1. -1 comma 1. Let's see what happens at 0. We've had mixed luck with 0 being something that's defined with our parent functions. So with the power function, we're going to put 0 in the base to the power of 4. Well, 0 times 0 times 0 times 0, we would only need 1 0 to get a product of 0. That goes through the origin. 0 comma 0. F at 1. Now we got to say, is this going to be the same or different from f at -1? So we'll set it up just as we had done. 1 to the power of 4 is 1 times 1 times 1 times 1, which is 1. And that, in fact, is the same output as -1. Notice there's a symmetry there that we'll talk more about later, but definitely we're seeing kind of a duplication there. Well, let's round this out by calculating f at 2. So that's 2 to the power of 4. And note that when I don't have negative signs, I can let that be out of the parentheses. So that's 4 times 4. If I pair those 2's up, 16. And that, again, shows a self-similarity when I've got a negative or a positive value of a number. -2 gives 16, +2 gives 16. Well, let's graph those. Now, I'm going to zoom down here. -2, 16 is way off my graph. In fact, it's almost off the page there. I'm going to try to place it there if you see on the upper part of that question. And we'll just use that kind of as a reference point. -1, 1, those here on the graph. 0, 0's there. 1, 1. And then 2, 18. Again, I'll place that way above. It's way off the graph. Well, let's sketch that curve. So I'm going to start here from these estimated reference points at 16. And this is a U-shaped curve. Note that the lower part of the curve is much more boxed than what we would see with something like a x squared, a parabola. So a rough curve in there, but we get the feeling about what the function looks like on the coordinate plane. And that completes that first task. Now we do need to analyze for these items. Now with the rational parent function, we saw 2 asymptotes, a vertical asymptote and a horizontal asymptote, but we had some parts in the graph, in the table, that were undefined. Nothing with this power function. Let's call this is the power parent function. In fact, we call it the quartic because it's to the power of 4, the quartic power parent. There's nothing undefined in terms of y. Notice we had outputs that really were just real easy to calculate. So there are no horizontal or vertical asymptotes for this parent function. Now, again, I can think in terms of the analysis. If I don't have a horizontal asymptote, don't have a vertical asymptote, that means I probably will have a y-intercept, probably will have a 0, an x-intercept. And the point that we're looking at is really one point that does both of those. The y-intercept is 0, 0. Notice that's where the graph crosses the y-axis. But what else is 0, 0? Good. It's also the x-intercept. So a lot of times if you've got a function that includes the origin, that's both its y-intercept and its x-intercept. Again, we call the x-intercept as 0. So that takes care of those two items. So the last thing that we need to describe is the domain and the range. So we'll pick up the domain green. Green is for x. The word green starts with x, right? Okay, domain. Now we need to think again horizontally for domain. So on the left-hand side, we're at infinity, negative infinity. Right-hand side, we're at positive infinity. With the quartic function, really with most power functions that are even, they look like a U. And the emphasis is that on this vertical growth. The question is, do they go to the left and to the right as they grow? Well, let's see if we can demonstrate that on Desmos. Let's see if we can plot the function. So I'm going to put in here f of x equals x to the power of 4. And let's see if we can zoom out and see, does the domain continue to grow to the left and the right as we zoom out? So on Desmos, to zoom out, if you go over to the right side of the graph, it's the minus button there. So I'm just going to zoom, 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 and click quite a bit. So definitely the vertical growth is more than the horizontal growth, but the horizontal growth never stops. It's a slow growth to the left and to the right. So if we head back to our note screen where we're doing this analysis, what we would have to conclude is that even though it's a slow growth, the domain is from negative infinity less than x less than positive infinity. Sometimes it takes a while to see that, especially when it looks like it's more vertical than horizontal. In interval notation, that's parentheses negative infinity, comma infinity. And the last thing for us, as always, is a description of the range. So that's the y, and that one's a little more easy to see than the domain for this quartic power parent. Note that the graph doesn't really exist in quadrants 3 or 4. So where the range picks up is right at that y-intercept, x-intercept point. So where we're picking up is at 0, right here on the x-axis, right where it's intersecting the y-axis. So it's from 0 is less than, now I got to be careful here. My y value actually equals 0. So I got to put the bar underneath the strict less than. So 0 is less than or equal to y is less than infinity. The upper part of the graph is still infinite. Now that's good because that allows us to see what do we do in interval notation if I can actually equal the value. The way I would write that is with a bracket, square bracket. So instead of parentheses, if I've got that equal option, it's bracket 0, comma, infinity. Infinity is always a strict less than because I can't equal a number that's always changing. So we would end that range with infinity, close parenthesis. All right, so that completes our graphing and analysis of 4 parent functions. Thank you for joining. I look forward to our next investigation of pre-calculus. See you soon.